Limits at the concept of infinity and horizontal asymptotes. In order to truly grasp the idea of limits in calculus, you have to be able to graph certain functions from algebra courses and certain functions from a trigonometry course or trigonometry experience. You want to be able to graph these from memory and from knowledge and from experience and procedures. Looking these things up will only make you draw them again and again without having to look them up. So make sure you could actually draw these graphs from memory and from knowledge, and then you have a really good chance of understanding limits in a differential calculus course. Our objectives for this topic is to evaluate more limits, gain the definition of a horizontal asymptote, find horizontal asymptotes, and if we have time, revisit the squeeze theorem. For the following examples, what you're going to do is actually graph the function from memory and observe the end behavior of every single function. So you may have done this in algebra, but we're going to do it again in differential calculus in greater detail. So exponential growth function, from left to right, it is actually increasing and concave up, and there is a y-intercept 0, 1. Now let's observe the end behavior. So as x approaches infinity in the negative direction, what happens to the corresponding function values? Now remember, we write this with limit notation. Notice this is actually approaching 0. And I'm going to conclude that, therefore, the horizontal asymptote for this function is actually the horizontal line called y equals 0. And we could see that, y equals 0 is actually labeled right here. Sometimes it is called the x-axis, but when we truly want to name it, we simply call it y equals 0. So there is the horizontal asymptote. We got to observe the other end behavior, the limit as x approaches positive infinity. What happens to the function e to the x? Notice it is actually approaching the concept of infinity. In other words, this limit does not exist. It is not a finite number. Infinity is not a finite number. So let's box all those observations. We could do similar observations for the function e to the opposite of x. Notice this is exponential decay. So from left to right is actually decreasing and it's concave up. The y-intercept is still the same. And let's go ahead and observe the end behavior. So this time, as x approaches infinity in the negative direction, the corresponding function values are actually approaching the concept of infinity. That means this limit does not exist. Let's observe the other end. As x approaches positive infinity, what happens to e to the opposite of x? This is actually approaching 0 again. And just like last time, we can conclude that, therefore, the horizontal asymptote for this function is once again y equals 0. You must write y equals 0. That is the name of the horizontal asymptote. In other words, if the horizontal asymptote introduced itself, it would say, my name is y equals 0. We could continue this observation of end behavior with trigonometric functions. So remember, you're graphing these from memory and knowledge. If you don't have them as knowledge yet, make sure you practice on your own and be able to graph these rather quickly without looking at anything. So you want to practice up to a certain point to realize, oh yeah, it's definitely part of my language, it's part of my vocabulary, and then you don't have to look things up by any means. I'm going to use NTS here. NTS stands for not to scale. And so there are the outputs for the inverse tangent function. Once again, we're going to observe the end behaviors by looking at the limits of the function. Let's look at the limit as x approaches negative infinity. What happens to the corresponding output values? This one is approaching negative pi over 2. What can we conclude? Therefore, the horizontal asymptote for this function, or I should say a horizontal asymptote for this function, is y equals negative pi over 2. Let's observe the other end behavior. The limit as x approaches positive infinity. What happens to the corresponding output values? They are in fact approaching pi over 2. And we have a similar conclusion. Therefore, another horizontal asymptote is y equals positive pi over 2. And this is all just from observing graphs from your memory and knowledge. Let's look at the trig function called cosine of x. This is a sinusoidal wave. And it's actually periodic. So this actually continues on and on and on and on. It just oscillates up and down, up and down. A standard period for the cosine wave is 2 pi. You cut it in half, you're at pi. You cut it in half again, you're at pi over 2. Pi over 2. So this is pi over 2, 2 pi over 2. This must be 3 pi over 2. I'm slightly off, but I'm pretty darn close to what I really wanted to intend. So I'm going to just make this mark bigger, and that's 3 pi over 2. This is negative 1. I'm going to go ahead and use NTS here for my trig functions. NTS stands for not to scale. Now let's observe the end behaviors. Let's look at the limit as x approach negative infinity, the far left end of this oscillating function. But because it's oscillating, it's never approaching a single finite number. It just keeps bouncing up and down. So we simply say this does not exist. That means there's no horizontal asymptote when you observe that end behavior as well. What happens as x approaches positive infinity? You can also see that this does not exist because it just keeps oscillating and bounces up and down. So no horizontal asymptotes for your trigonometric function called cosine of x. What about the natural log function from your algebra experience? Remember, graph this from knowledge and from memory. You got to know that it bends like this. From left to right, it is increasing and concave down. It has a y-intercept of 0, 1. I'm sorry, I meant to say x-intercept of 0, 1. And so there is your natural log function. And we'll observe the end behavior. Now, when you observe the end behavior, we're going to look at the left-hand side limit, which means x is approaching 0 from the right side or from the positive side. And we want to observe that end behavior for the natural log of x. So as x approaches 0 from the right side, where do the corresponding function values go? The corresponding function values are actually going to negative infinity. Now, is negative infinity a finite number? Certainly not. So we can actually conclude that this limit does not exist. Okay, it's approaching the concept of negative infinity. However, we could say something here. I might as well say it. Therefore, a vertical asymptote is what? Is x equals 0. And there's the vertical asymptote. So very different from previous examples, yet all we're doing is observing graphs from your memory. Let's observe the other end behavior. Let's look at the limit as x goes to positive infinity of this function called natural log of x. Notice this just continues the increase and will continue to approach positive infinity. As x approaches very large, the corresponding y values are getting very large in the y direction. So that is actually going to go to the concept of infinity. Once again, this limit does not exist. All right. So what can you conclude about certain end behaviors? Well, here's a formal definition. Here's a formal definition of a horizontal asymptote. If the limit as x approaches very large of a certain function gets to a finite number L, then we say y equals L is a horizontal asymptote of f of x. Analogously, if x approaches very large in the negative direction of a certain function called f of x, and it approaches a finite number called m, then we can say y equals m is a horizontal asymptote of f of x. So from the previous examples, can you spot how this formal definition is being written out just from observations? Go ahead and do that.